Hey everyone, it's Mr. Canfield. I'm going to be going through chapter 7.1 today, dilations. So I brought a couple extra colors with me, and you may even want to bring a ruler with you when you do this. So let's get into it. So we have two images here. How are they similar? How are they different? Well, obviously one's bigger than the other. The similarities though, it's the same shape, right? It's just shrunk down. And if we were to get a little bit more detailed, it's like every little piece of this is the same. Like the shape of the eye is exactly the same. The shape of the teeth are exactly the same. This is called a dilation when it's scaled down and it keeps the relationship the same, the proportion is the same. That's what a dilation is. Let's say we took it and we squished it, but like it was a little wonky, like we didn't do it perfectly. That's not a dilation anymore. So that's, in math, that's what we call a dilation. It's a squish down or a blow up. It can go in either direction. So if you want to follow a way using the rulers, you can use the directions in here. I'm gonna give you the down and dirty, quick way to do problems like this. We're going to dilate about this center point by a factor of 2. And so the way we can do that is simply by counting. So here, 1, 2 spaces over, 1 space up, right? That's what that took. If I want to dilate by a factor of 2, I take those directions and I multiply them by that factor of 2. So instead of going 2, I'll do 2 times 2, which is 4. So 1, 2, 3, 4 over. And then instead of going 1 up, we'll multiply that by 2, and we'll go up 2. So instead of going over 2, up 1, now I'm gonna go over 4 and up 2, and I'm gonna put a dot there, and that's called B prime, because the first one was B. So I got that one. Now, how do we get from the center to C? Well, we counted over 1, 2. We counted over 2 spaces. So all I have to do is multiply it by the dilation factor of 2. So 2 times 2 is 4. So instead of 1, 2, we're going to go 1, 2, 3, 4. We'll call that C prime. And then to get to A, we went down 1. And again, since we went down 1, we'll double that. We'll go down 2 instead and put a dot. And if we connect the dots in this situation, it's almost like I should have brought a ruler with me. If we connect the dots in this situation, you'll notice that the new picture is very similar to the old picture. It's just stretched out, which is the whole point. So you can use a ruler on these things, you cannot use a ruler on these things. It doesn't matter to me. The main thing that I care about is that the points are clear. Oh wait, yeah, this is A prime. So, and generally what we're gonna do is whenever we do one of these transformations, we're gonna do a little color code off to the side. This was D2, right? We dilated by a factor of 2. So I'm gonna try to do that consistently whenever we're drawing these things. Let's continue on. All right. So now we're gonna do a dilation about this point M, and it says this time the factor is 1/3. So again, you can do this with a ruler, but I really like just doing it by counting. So if we're dilating by 1/3, well, let's see what happens. 1, 2, 3. This was 3 spaces down. So I'll take my 3 spaces times 1/3, which you can use your calculator to do, or if you remember, when we multiply by a fraction smaller than 1, 3 times 1/3, that's the same as saying 3 divided by the bottom number there. So 3 divided by 3, which is just 1. So instead of going down 3 spaces, I'll go down 1 spaces. Let me switch, let me try to use a fun color. So we'll go down 1 space and put a dot. Then what about over here? Well, if I count out carefully, 1, 2, 3 down, and then 1, 2, 3, 4, 5, 6 over. So 3 down, 6 over. I'll divide each of those by 3 and get 1, and 6 divided by 3 is 2. So now I'll go down 1 space and over 2 spaces, and that is, are you out of ink already? I just started using you. Okay, there we go. So this one up here was C prime, this one was B prime, and then now let's deal with A prime. Oh, it's all the way down here. So again, I'll count from M down to A. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 down. And then 1, 2, 3, 4, 5, 6 over. Oh, just like that one. So it'll be 2 over because that was 6 over down to 2. And then 9 divided by 3 is 3. So instead of going 9 down, 6 over, we'll go 3 down, 2 over. There's our C prime. All right, and there is our dilation. So that's dilations in a nutshell. One thing that's worth pointing out right now, what's that angle right there? We got a right angle. Notice how it's still a right angle. And if we were going to measure all these angles, all the angles would match. That always happens in a dilation. So sides, and they changed proportionally. And what that means is they all changed in the same ratio, the same amount. They all cut into a third of their original self. It's always going to be some kind of scaling up or down by the same amount. And what stayed the same? The angles. So huge idea number one. In dilations, the angles stay the same, but the sides are proportional by the scale factor, or you could say scaled, multiplied, whatever works for you there, whatever helps you understand. I'm trying to make these quick notes for you, so if you do run into any questions, please let me know, either in the comments or email me. All right, so this is very faint. So faint that I don't know why I gave this to my students. I should have made it a better copy. All right, so it's asking, is this very faint rectangle a dilation of the original one? All right, so that's all filled. This is a filled in rectangle. I just darkened some of the graph paper for me to read it a little bit better. Okay, so originally this is 2 spaces, I think, 2 spaces by 3 spaces. Let's see what it turns into. 1, 2, 3, 4, 5, 6 on this side, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 on this side. So 2 and 3 to a 6 by 9. Well, let's think about that. What's our scale factor to get from 2 to 6? And another way to say that is, what did I multiply 2 by to turn it into 6? So if you can see it, oh, it's 3. If you can't see it, to find the scale factor, all you need to do to find scale factor is take the new side divided by the original side. So my new side is 6. My original side is 2. 6 divided by 2 is 3. Okay. If that truly is a scale factor, then for every other side, it's going to work out. So 2 times 3 is 6. What's 3 times 3? 9. What's 2 times 3? 6. What's 3 times 3? 9. Since it was 3 for all of them, it's a consistent scale factor. So since the scale factor is 3 for all of them, and if we look at the angles, it's a rectangle, so it's got all right angles. This is a rectangle, it's got all right angles. So boom. Are all the angles the same? Yes. Scale factor is 3. It is a dilation. This one is tricky to read. This one looks like it's 2 by 1. It's hard to tell. Well, you know what? This is for your own notes and for your own learning. So let's just say it's this. Let's see, 1, 2, 3, 4, 5, 6 along the bottom, and 1, 2, 3 along the side. And then its potential dilation is 2 on this side and 1 on this side. Well, how do I get from 3 to 1? I multiply 3, but no, 3 needs to get smaller. So I could say, well, I take 3 and I divide it by 3, which if we're trying to say that as multiplication, we could say 3 times 1/3. So 3 times 1/3 gets me 1. Well, does 6 times 1/3 get me 2? Or does 6 divided by 3 get me 2? It really is the same question. Oh, it does. And they're all right angles. So yeah, these are dilations. This is a dilation. Dilations are allowed to be shrink down. They can be blow up or shrink down. I understand that was not very good English, but that's okay. All right. Let's look at our next one. It just says find scale factor for these. So if I want to find the scale factor, the idea is that these are similar figures. So I've got 12 here, I've got 18 here, and it looks like this is the prime one. This is the dilation. So that means that all I need to do is figure out what do I need to multiply 12 by to get 18. And a very easy way to do that is to divide the new side by the old side. So 18 divided by 12, and you can use your calculator, you can use your brain, you can look it up on Google, which is the same thing as using a calculator. That's 18 over 12. I'm gonna do it out on paper. So 18 over 12, new divided by old. Let's see, they're both divisible by 2. So divide the top by 2, I get 9. Divide the bottom by 2, I get 6. And those are both divisible by 3. So if we divide them both by 3, I'll get 3 and 2. So my scale factor is 3 over 2, or 1.5. I accept either one. And we would do the same thing here. We would find our side length. Looks like this one's 2 and this one's 1. So it's shrinking. So I know that to get from 2 to 1, we'll divide by 2. So our scale factor will be 1/2. Was that too fast? If you answered me, that's very strange because we are not actually having a conversation right now. You are watching a video. So a scale factor over 1 is, well, let's see, under 1. And what I really mean by, this is called an enlargement. But like any synonym for big, getting bigger is fine with me. I think the math word is enlargement, but doesn't really matter. And then under 1, this is really saying between 0 and 1. And technically including between 0 and -1 as well. But under 1 is called a reduction. But you can put shrink or whatever. All right. So we actually can do this without any drawing, without any counting. We can do it completely just by, if you know the original coordinates and know what you're doing, then it just works. So all the lines are absent here. I'm gonna say it's 1, 2, 3. So I'm gonna say that A is the point 2, -1, because we went 2 over down 1 is what I'm estimating this to be. Point B is to the left 1 and up 2. That's -1, 2. And the point C is 3 over, and that's it. So that's 3, 0. If I want to dilate this by a factor of 3, all I have to do is literally take these coordinates times my scale factor of 3. And I multiply them all individually. So 2 times 3 is 6. -1 times 3 is -3. And go try it, see if it makes sense to you. -3 times -1 is -3. 3 times 1 is 6. 3 times 3 is 9. 3 times 0 is still 0. So I don't even have enough room to graph it all, but that's what the points would be. Some of my students really like writing the points and doing the math on it. Other students like to draw it. And it's a matter of preference. What do you like to do with this? What's more comfortable for you? So for this one, we're gonna do a reduction, and I can kind of see where my lines are. Oh, and it's got the markings too. So it looks like this is at, Q is at 11, -4, I believe. No, it's at 12, isn't it? Because that's 11 there, and then that's 12. So that's at 12, -4. P is at 8, 4. And R is at -4, 0. Okay. So then let's do our dilation. It says we're going to multiply by 1/4, which remember, that's the same as divide them all by 4. So just divide each number individually by 4. So that's 2, 1, 3, -1, -1, 0. And I could actually like draw it out like I have been doing before, and then divide the directions and stuff, and it'll work. Like on this one, I went 4 to the left. So that if I divide that by 4, that's 1 to the left. That's this point here, -1, 0. This one, I go up 4 over 8. So if I divide both of those by 4, instead of going up 4, I'll go up 1. Instead of going over 8, I'll go over 2. That's this point right here, 2, 1. When I was doing the directions, I went up first, but coordinates always do x first. And then if I'm trying to get to Q, well, I can go up 12 and down 4. Divide that by 4. I'll go over 3 and down 4. 4, no, 3. Go over 3 and down 1. It's silly. And so you can see that those coordinates are all the coordinates I just got through a different means. Yeah. All right, let's see. What's our last question? A blueprint for a new library uses a scale factor of 1/50th. So that means that you take the original, divide it by 50, you have the blueprint. Mr. Iyer measures the reading space on the blueprint to find the actual dimensions and area so he can order furniture. What are the actual dimensions of the reading space? Okay, so if this is the reading space, looks like it's 12 by 12 inches. Centimeters, okay. So this is 12 centimeters by 12 centimeters. That's 144 centimeters squared. So the thing is, if we're gonna scale this up, the actual dimensions aren't 12 by 12. The actual dimensions are 12 by 50. So 12 times 50, I mean. So 12 times 50, this is the small version, we wanna blow it back up. Is what, 600? So 600 by 600, so then that's 360,000 centimeters squared. Oh, I did both problems. So how does 360,000 compare to 144? Because I don't know about you, I was kind of expecting to be 50 more. Is 50 times, is 360,000 50 times 144? Check it out. So, spoiler alert, I'm going to tell you. 144 doesn't get multiplied by 50. 144 gets multiplied by 50 twice because each of the dimensions individually got scaled up. And so you actually scale this twice. You scale it once for that and scale it again for that. All right. Hope that was helpful. And I'll see you on the next one.